in this chapter, in this exercise, we're going to introduce the standard normal distribution. So a standard normal distribution is a normal distribution with mean 0 and variance 1. So this is what we call the standard normal distribution. And notice that it has mean 0 and standard deviation, and variance is equal to 1 as well, because you square 1 to get variance 1. So that's what this distribution looks like. A bit of notation that we need to know is we generally call a random variable which follows this distribution, we generally call it Z, capital Z. So here we've got a random variable Z which follows this distribution, and our values of Z go along the horizontal axis. Some notation that you need to know is if you've got a value A here, and we want to work out what's the probability of Z being less than A, we could write that as the probability of Z being less than A, obviously, and we could work out what that is using inverse normal on our calculators. But a bit of notation that you need to know is that you can also write this as phi of A. Okay, so phi of A is the probability of Z, our standard normal variable, being less than A. So for example, if you wanted to work out what's the probability of Z being greater than 0.9, for example, we wanted this probability here, and we wanted it in terms of phi. Well, we know that the probability of Z being greater than 0.9, phi is always to do with the left of a value. So we need to write this as in terms of the probability of Z being less than something. Well, we could write this as 1 minus the probability of Z being less than 0.9. And the reason why is because we know the total probability underneath the curve adds up to 1. So this shaded area here is equivalent to doing 1 subtracted the shaded area to the left of 0.9. So this basically says 1 minus the probability to the left of 0.9. Well, the reason why we've done that is because we wanted to write it in terms of this phi function, and the probability of Z being less than 0.9 is the same as phi of 0.9. Okay, so we're going to use this later on. The reason why we have introduced this is to do something called coding. Well, it turns out that if you have a normal random variable, say with mean mu and variance sigma squared, you can do something called coding, or another word is transforming, or standardizing. You can do a transformation of X which is going to follow this standard normal distribution. So what we're going to do in order to standardize is we're going to take our X variable and we'd need to take away mu and divide by sigma. And it turns out that this random variable here follows a normal distribution with mean 0 and standard deviation 1. That's always true. And so we often call this Z because Z means standard normal random variable. So what we've got is we've got this original distribution of X with mu in the middle, and we've transformed it, and we know that if we put Z on the horizontal axis here, we've got 0 in the middle here. So let's look at a specific example. Let's suppose we had X follows a normal distribution with mean 20 and variance 3 squared. So standard deviation is 3. And let's say that we wanted to find out what's the probability of X being less than 13. Okay, so we could work that out in our calculators. standard deviation is 3, and the mean is 20. And we get that probability is 0.0098. Okay, well, another way of doing this would be to standardize and work with our random variable z instead of x. So let's standardize. So we're going to say that z is equal to x, and we need to take away the mean of the distribution, which is 20, and divide by the standard deviation of the distribution, which is 3. And we know that that variable there, this standardized variable, will follow a normal distribution with mean 0 and standard deviation 1. So we still want to find out what's the probability of x being less than 13. Well, we need to standardize this 13 in order to work out what z would be, because it's not going to be 13. So let's take this probability statement here and let's transform it into a z probability statement. So if we start with probability of x being less than 13, what we want to do is we want to get it in terms of this z variable, which is normal 0, 1. So in order to standardize it, we need to take away the mean from both sides and divide by the standard deviation on both sides. And we've done that because on the left hand side now we've got this random variable z, because that's our definition of z. Take away the mean and divide by sigma. And we can work out what 13 minus 20 divided by 3 is, which is minus 2.33 dot dot dot. So we could check that that actually gave the same answer. So the probability of z being less than minus 2.33, we're going to put our lower this time as minus 2.33. And because we're working with z, our standard deviation of z is 1 and the mean of z is 0. And we do get the same answer of 0.00981. Another way of thinking about this would be we need to transform this 13 using our transformation. And our transformation is we take away mu, take away our mean, which is 20, and divide by our standard deviation, which is 3. So we'd get that value there that we want to work out the probability to the left of it is, we get that as minus 2.33 when we transform it. So we can have a look at this example then. And we've got this random variable x which follows this normal distribution, and we want to write each of these probabilities in terms of this phi function here. So let's start with our random variable x, and let's just write down what mu and sigma squared is. So mu is the mean, which is 50. Sigma squared, our variance, is 4 squared, so our standard deviation is 4. So if we were to draw a sketch of this x random variable, we know that we'd have 50 in the middle, and we want the probability of x being less than 53. So we'd put in 53, and we would shade in the region to the left of 53 because we want x is less than 53. We could work out that probability using our calculators. And if you do that, you get that this shaded area is 0.773. So we're not actually asked for that, but you can use that to check later on. What we're asked to do is we're asked to transform it into this z variable here. So we're gonna transform it, and we're gonna try and write this as a probability statement in terms of Z. So there's two ways of doing this. One way would be to transform this 53, because when we're working with normal 0, 1 for our Z distribution, it won't be 53. So in order to transform 53, we need to take away the mean, which is 50, take away mu, and divide by the standard deviation, which is 4. And that's going to get us our standardized value, which will be 0.75. So that's one way of doing it. The way that I think makes a bit more sense is to start with your probability statement to do with x and try and get z into this. So remember, z is going to be x minus mu over sigma. So in this case, z is going to be x minus 50 divided by 4. So in order to get that on the left hand side, we're going to take away 50 from both sides. And then we're going to divide both sides by the standard deviation, which is 4. Well, we've done that because on the left-hand side of this inequality, we've got our random variable z, our standard normal random variable, and we can just work out what the value of the right-hand side is, and we do get 0.75. So that means that we want to work out the probability of our standard normal variable z being less than 0.75. That's what we found there. Well, that is just phi of 0.75. Remember what the definition of phi was. It's the probability of z being less than this value here. 50 in the middle still, and we've got 55. And we want the probability of x being greater than 55. What's that probability? Well, we're going to transform it into a standard normal variable. This is our z, which is normally distributed with mean 0 and standard deviation 1. And we need to try and find out what this 55 transforms to when I standardize it. So in order to standardize it, I'm going to take my 55, I'm going to subtract the mu of x, the mean of x, which is 50, and divide by the standard deviation. So this is equivalent to saying what's the probability of z being bigger than 1.25. Another way of saying that, which is the method that I use, is I start with the probability statement to do with x, and somehow I need to try and get my z variable into this inequality. And remember, z, the transformation is we're going to take away the mean, which is 50, and divide by the standard deviation, which is 4. So let's take away 50 from both sides, and then divide both sides by the standard deviation of x, which is 4. And the reason why I've done that is because now I've got the probability of this variable here, random variable, is z, by definition of z. And that's greater than or equal to 1.25 on the right hand side. Now, we weren't asked for that, we were asked to put it in terms of this function here. So in terms of this, remember this function is what's the probability to the left of a given value? Well, we've got the probability to the right of a given value. But notice that I can write this as 1 minus the probability of being to the left of 1.25. Because this area here is 1 minus this area here, because the total areas add up to 1. And now I can write it in terms of phi, because this is our phi function of 1.25. Because remember, this is just exactly the same as that, they're the same as each other.